This is an irrigation-related topic called pressure bombs or pressure chambers. And we're measuring water potential. And it's measuring the potential or tension of water inside of the plant's tissues. And it's something that's done for a lot of crops for research purposes, and higher value crops. The higher the value, the more likely it's done for commercial purposes. And so as you see here, actually there's a video going at the moment. There's a number of videos that show various aspects of this. They're short videos and some other resources that I haven't even double checked at the moment. I know that all of these other videos are good because of the links are showing a picture. I'm not going to bother with these. Don't worry about trying to memorize or study, take notes on all of these other videos. This is just something you can take a peek, look at these things. The more interested you are, the more time you should spend on it. But it is good to see how different people present the topic. As soon as I'm done with this lecture, I will put it in right here underneath the very first one and have my video lecture right here. So let's go to the PowerPoint. Pressure chambers. And actually, hold on a second. I think I've changed my mind for a moment. Let me just show you something really quickly and show you what this person is doing. They are taking a leaf sample, and I've got the video muted here, but you can see he's taken a leaf sample, put it in a plastic bag, and attached the petiole of the leaf to a device that he's going to lock tight with a gasket, so it's an airtight pressure chamber. And come on. Of course, my video is going to give me problems now. And so then he pumps the device up. In this case, he's using just a pump, like a bicycle pump concept, to get the pressure up in the chamber until he sees some liquid, some water coming out, or it wouldn't be water, actually, it'd be the phloem juices coming out of the petiole cut end. And as soon as you see it start to bubble, and here it is, all right, it's starting to bubble. You can see a little bit of water, and boom, there it comes. So that's the key, and he measures the pressure on the device at that moment. And so the measurement of the water pressure at that moment when water starts coming out would tell the user how much pressure did it take to force the water out of the leaf. The more pressure it takes to force the water out of the leaf, the more water stress the leaf is under. Now, you can't compare, you know, a lettuce leaf to a corn leaf to a grape leaf. They all have their different numbers, but they fall within a relatively modest range. But you can't just automatically compare among different crops. So that's the basics of what we're talking about here. So in the early 20th century, this concept was first pioneered. You don't have to memorize the details on the history of it, but it is now a process that has been revived, brought back into the mainstream for measuring plant moisture stress. And you use this as a combination of three tools primarily. Number one, your pressure chambers that we're talking about. Number two, evapotranspiration. What's the weather telling you? How much water have you lost? And number three, soil moisture probes of some sort, like a tensiometer, something of that sort. You put those three things together to give you a full picture of what's going on in your irrigation management system, and you determine from there when to water and how much to water. So what is a pressure bomb and why use it? It's an instrument that can be used in the field to measure plant water potential. The one that I have in the lab at Hartnell is more like a very bulky travel personal suitcase. It's not the size of a full-size suitcase, but it's bigger than just a little overhead compartment, airline overhead compartment suitcase. It would not quite fit in the overhead bin. And instead of using a bicycle pump style design like you just saw in that brief video segment, it has compressed nitrogen gas. And so you just turn a valve to release some of the nitrogen to pressurize the chamber with the leaf. But you're measuring plant water tension. The water in leaves is under tension, negative pressure. The water in the roots by osmosis ends up being under positive pressure to help push that water up. But inside the xylem, it actually is considered under negative pressure, and it takes a positive pressure of this pressure chamber, or pressure bomb as it's called affectionately in industry. So it takes positive pressure inside this sealed chamber of the pressure bomb to push the water, the phloem fluid, out of the leaf petiole at the cut end. So there are 4 primary ways to measure plant water potential. Stem water potential. It says here the best method. That's something that the author of this decided based on their criteria. It doesn't mean it's the best method for everything. It's just one of the more common, more universally good methods that gives good, reliable data. We'll talk about that in a minute. Leaf water potential, pre-dawn leaf water potential, that's pretty obvious. You're taking it before the sun hits it. And shaded leaf water potential. So you're taking a leaf, if it was grapes, you're taking a leaf from the bottom or lower part of the canopy or inside the canopy rather than in full sun. But whatever method you use, you just have to play around with it, validate it, find out what works for you, and it helps growers, farming consultants, vineyard managers to save water, reduce irrigation costs, improve growth, sustain higher crop productivity, while reducing loss and increasing the lifespan of their plants. Because you're getting one more piece of information that can help you fine-tune your water and not just have, well, how much water does my ETO tell me, or ET crop, ETC actually. What is my evapotranspiration telling me? That's a mathematical calculated estimate, and it could be off by a little bit. What is my soil moisture telling me? Well, that's important to know, but it doesn't tell you how much of that water actually got into the vine. So those 2 other pieces, evapotranspiration and soil moisture, are important to know, but it really helps if you also know the actual water tension or potential in your vines. So let's look at a couple of these. The stem water potential. You take this at midday when the water demand and photosynthetic activity are at a maximum. You put a plastic bag or foil around the leaf in the lower canopy. It's a shaded leaf to minimize heating effects. So stem water potential, you are doing it midday, but in the shade. And you leave that plastic bag or foil on for 10 minutes to 2 hours, depending on your experiments, the data you're collecting, what kind of crop you're dealing with. 10's the most common, certainly it's most efficient. Leaving these on for 2 hours is a logistical nightmare if you're running around doing this to a lot of fields, right, or vineyards. This effectively stops natural transpiration because you put it in a bag or a foil pouch. Transpiration stops. And so the water potential in that sealed bagged leaf is going to come into equilibrium with the stem. Whatever the stem is, given 10 minutes to 2 hours, the leaf water potential will reach an equilibrium or balance with whatever's in the stem or shoot, cane, whatever. So it's a good way to see what's going on in the stem indirectly by measuring the water in the equilibrated leaf petiole. This measurement is less susceptible to fluctuations in environmental pressures than the leaf moisture, than the leaf, and more representative of actual leaf stress in the entire plant. So that's why this one is called the best by the author of this. It does have advantages. You're measuring it when the plant is in midday at its peak use, and you find out what the real stress might be. Leaf water potential is also a midday measurement, but you take a fully expanded or full size mature leaf, not an old one, but one that's just recently to full size, and it's exposed to direct sunlight as opposed to shade. You quickly bag to avoid any further transpiration, cut it off or excise it, and immediately test in the chamber. So you're testing the leaf in the sun in the midday without giving it time to equilibrate with the stem. You're not putting it in a bag for any length of time to allow that equilibration to occur. You're stick it in a bag, cut it off, measure it, boom. It's quick, that's an advantage, but it can be highly variable among different leaves on the same plant because different leaves getting different sun exposure, and you can't get completely accurate sun exposure on everything. It's a challenge, it really is, to get consistent numbers. And the bottom line is they often aren't consistent numbers. But despite this variability, science has shown this to be useful as an irrigation scheduling tool for wine grapes and cotton. Here we are in grapes. So the leaf water potential, despite the variation in the data you get, with a good strategy for sampling and a consistent person doing this, you can get good, reliable data, and it can be very, very useful for going through large numbers of vineyard blocks and making estimates. So despite the stem water potential having the reputation as the best, the wine industry and the people I've talked to in the wine industry would concur that leaf water potential is the one that they tend to go to. But I haven't talked to enough people to have any stats on it. I maybe just talked to the wrong people. But certainly I've talked to enough people to know that in the wine industry, there's definitely people that think this is a good way to go. Then there's a couple of other measurements. I'm not going to go into the detail. Pre-dawn leaf water potential, same as the leaf water potential, but taken before the sun hits it. Shaded leaf water potential, also similar to the stem water potential, but the leaf is covered with a damp cloth instead of plastic and foil. Again, just some variations in technique. The first two are the only ones I really care that you think about, since one is the best, as they say, the most common, certainly in lots of different industries. And the second one, the leaf water potential, being the one I know of in grapes that's being used by the people I know. So what about pressure chamber safety? Depending on the species under study, the pressures in the chamber can get over 500 PSI. That's why they call it a pressure bomb. 500 PSI, if a seal breaks, if a chamber cracks and a piece comes off of it, that can be like a bullet. We actually had a stem, a petiole actually, of a leaf be separated from the leaf and shoot out through the top and probably go up 8-10 feet and smack the ceiling in the room. If that was you staring down without goggles on and that went into your eye, could have done some serious damage to somebody's eyes. So you wear safety glasses, period. You do not do this without safety glasses, and you make sure you have a high quality chamber that's made for this task and made for the pressure ranges that you're dealing with. Some chambers just, you can't do 500 PSI in some of the pressure bombs out there. They're not designed to take that much pressure. Anyway, be very careful. They are potentially quite dangerous if you take them too casually. So, 1 bar. A bar is a measurement of pressure. And a lot of people think of pressure as pounds per square inch. That is a number that's often used in the United States when we're filling our car tires. Well, what do you do with the car tire? Oh, our front tires are, 32 PSI, the back ones are 35 PSI, or, my 10-speed is 85 PSI, my mountain bike is 55 PSI. Different tires need different PSIs. So if you've done inflating tires and sports balls, the your football, basketball, soccer ball, volleyball, they're going to be down there 3 to 6 PSI, I think, is a typical range for various sporting balls. So we're used to that. But we're not used to bars. We're not used to pascals in our day-to-day life unless you've had some exposure. But those are different measures, and 1 bar is equivalent to 14.5 pounds per square inch, PSI. 10 bars is the same as 1 megapascal. So again, I'm not going to test you on those numbers, but I want you to be familiar with them. And if you ever use these, you need to be able to look at the literature, and maybe one paper talks about PSI, another paper talks about pascals, another paper talks about bars of pressure, or your device, the meter, the gauge, the pressure gauge is in one unit and your paper that you have to report is in another unit. It's easy to make the conversions if you know them. They're right there. There's the conversions. Anyway, but since the water in the plants is under negative pressure or tension, the scientific convention is to express water potential pressures in negative values, because you're creating a positive pressure in the chamber in order to push the water out, which is under negative pressure inside the leaf and petiole. Small numbers mean less stress. It takes less pressure to push the water out. If it takes less pressure to push the water out, that means there's more water. It's easier to push the water out. When there's not very much water in a leaf and petiole, when it's under a lot of stress, water stress, it takes more pressure to push that out. So again, small numbers, low stress. Large numbers, more stress. And with that, I'm going to take a 2-second break.